Hi, this is Jeff Spence, your Math 135 instructor for the Community College of Denver. And this is our video lecture over the distribution of the sample mean. So this is our beginning to Unit 3 in the course. Unit 1 was just the introduction to statistics. Unit 2 was computing probability and understanding probability distributions. Now we're going to start to get into the inference part of the course, where we're trying to use our statistics to make a better judgment about the population. One of the big things we talked about in Unit 1 was that if we don't know the population mean and we want to figure out what it is, we can use the sample mean. We can conduct a sample and compute the sample mean and use that as an estimate of the population mean. So with that in mind, it's important to understand the distribution of the sample mean, which once again is used to estimate the population mean. So if we look at how the behavior, in other words, of the sample mean, it'll give us a better idea how good of a sample mean the estimate, or how good the sample mean is as an estimate of the population mean. So let's start here. So statistics such as x bar, the sample mean, are random variables since their value varies from sample to sample. So one person who does a sample of the number of hours that people work at CCD could be different from another person's sample of people who ask how many hours do you work per week for students at CCD. So as such, they have probability distributions associated with them because there can be different values for the x bar that could have come from the population. And it's a random variable. Random just means you don't know what you're going to get. Variable just means it could be different values. So in this chapter, we focus on the shape, center, and spread of statistics such as x bar, the sample mean. So the shape, it's going to turn out, it's going to be bell-shaped, and then we'll talk about the center and the spread, which is the mean and the standard deviation of the bell curve. So the sampling distribution of a statistic is the probability distribution for all possible values of the statistic computed from a sample of size n. So the big idea here is that whenever you're computing a statistic, you have a sample of size n, and then we will look at the distribution of theoretically all possible samples that we can get of size n from the population, and then how does all the different sample means that we get from all those different samples, how is it distributed? And that's called the sampling distribution. So for instance, the sampling distribution of the sample mean is the probability distribution of all possible values of the random variable, the sample mean, computed from a sample size n with a population with mean mu and standard deviation sigma. So how this works is that you pick your sample size and obtain that random sample. Then you compute the sample mean. And theoretically, this is the idea that we're supposed to be able to do this over and over again so we get all the samples of size n from this population. Let me press pause for 1 sec. So first we're just going to describe the distribution when we sample from a normal population. So the thing is that certain variables, like we said, are normal, like bell-shaped, and some variables aren't. They could be skewed right or skewed left. The first objective that we're going to deal with is assuming we're sampling from a distribution that's normal. So variables like height, weight, SAT scores, a lot of the variables we were looking at in Unit 2 when we're doing the normal distribution problems. So let's say we're going to sample from a variable, a population that's normally distributed. So here's an example. They say the weights of pennies minted after 1982 are approximately normally distributed with a mean of 2.46 grams and a standard deviation of 0.02 grams. So that just means most of the pennies are very close to 2.46 when we have a bell shape, or 2.46 grams, and we have a bell shape around that weight. Approximate the sampling distribution of the sample mean by obtaining 200 simple random samples of size n equal 5 from this population. So what they're trying to do here is just show you that if we actually got 200 different sample means from a sample of size 5, where would those sample means end up? What would the distribution look like? So they do all this work and they're like, okay, yeah, we do a sample size 5, we get a mean, etc. Here's like 5 penny weights. And then they're like, oh wow, look at this is the 200 different sample means from the 200 different samples from the 5 pennies that they. So each one of these numbers is an average of 5 pennies weights, and they have 2 different 200 different averages from 5 different pennies. And when we look at this, they computed this, that the mean of the 200 sample means is 2.46, which is exactly the same as the population mean. And the standard deviation, though, is much smaller than the previous standard deviation because the standard deviation used to be 0.02. Now they found the standard deviation of the sample means was 0.0086. So then here's the distribution. So what they're finding is most of the sample means were right about here, and that's about 2.46. And it's looking like, based on a sample size 5, 200 different samples, that the mean, the distribution of 200 different sample means looks to be pretty bell-shaped. So the second question that they're going to ask is, well, what happens if we get a larger sample size? What role does n, the sample size, play in the standard deviation of the distribution of the sample mean? As the sample size increases, the standard deviation of the distribution of the sample mean decreases. So they're going to illustrate that here. So let's say now that we have sample size 20, we're going to do the exact same thing. We're going to do 200 samples, but last time we had sample size 5. This time we have sample size 20. 20 different pennies. And here's the distribution. And what they're showing here is, okay, once again it's bell-shaped. It's centered right at 2.46, which is the population mean, the mean of all pennies. And then it says, but the standard deviation now is 0.0045. It used to be 0.0086 for a sample of size 5. And the reason is that basically what this says, it's kind of illustrating what's called the central limit theorem, is that as our sample size gets bigger, the distribution of the sample means just becomes more concentrated towards the center. In other words, averages, when you get a bigger sample, the average tends to cluster towards the middle of the distribution. In the middle of that distribution is the population mean. So that's what this is showing here. So generally speaking, this is basically the beginning of the idea of what's called the central limit. So suppose that a simple random sample of size n is drawn from a large population. Now keep in mind, this is a large population that's already normally distributed. That's the case that we're dealing with here, with mean mu and standard deviation sigma. The sampling distribution of x bar will have a mean equal to the population mean. So what this is saying is that the mean of the sample means, in other words, the center of that distribution, is equal to the population mean. And the standard deviation is equal to the standard deviation of the population divided by the square root of n. And when we divide by the square root of n, what we're showing here is as the sample size gets bigger, the standard deviation of the distribution of sample means gets smaller because we're dividing by a bigger and bigger number. So it says the standard deviation of the sampling distribution of x bar is called the standard error of the mean and is denoted sigma x bar. I won't use that term very often, but they call this the standard error of the mean. But the big thing is that what we're saying here is that the distribution of the sample mean is the mean of that distribution is equal to the population mean. And that's really, really important because the sample mean is meant to estimate the population mean. So if the distribution of the sample mean is centered at the population mean, the thing that it's supposed to estimate, that means that that's a good thing because the sample mean generally in a normal distribution, observations are close to the middle. And if the middle is the thing that you're trying to estimate, then you're going to have a good estimate. So let's see here. What are we covering here? Let me press pause. So this is just hammering home the point that if the random variable x is normally distributed, the distribution of the sample mean is normally distributed no matter what, no matter the sample size. And we know that it has the mean equal to the population mean and the standard deviation equal to the population standard deviation divided by the square root of n. So let's just look at an example here where we would use this information from computing probability. So here we have the same distribution of pennies. The mean is 2.46 grams, the standard deviation is 0.02 grams. What's the probability that in a simple random sample of 10 pennies, oops, geez, I didn't mean to do that, sorry, minted after 1982, that we obtain a simple random sample mean of at least 2.465 grams. So We already know the distribution of the sample mean is normally distributed. It has the mean equal to the population mean, and the standard deviation is equal to the population standard deviation of 0.02 divided by the square root of n, which is 0.0063. So if we want to find the probability that the average of 10 pennies is going to be above 2.465, we do the z-score. So 2.465 minus the mean divided by the standard deviation, which we obtained here, 0.79. Now they don't use normal CDF in this, but we would just do probability that z is greater than 0.79 is normal CDF, 0.79, E99. They're doing the old school approach from the table, and they get the probability of 0.2148. So this will be an example we're going to do in the reading assignment or the video assignment. Okay, then the second part of this, which we won't spend as much time on, is when we sample from a non-normal population. So let's say that the distribution isn't pennies that are already normally distributed, but something that's not normally distributed, like something like ages or something could be skewed right, or different variables aren't necessarily bell-shaped. So if we're sampling from that distribution, we also want to make sure that the distribution of the sample mean is still normal, but we have to make sure, we have to do something to make sure that happens. So here they're just showing a distribution that's not normally distributed. It's a uniform distribution that if you looked at the frequency of different numbers on a die, they would all be equal, 1/6. And so they're saying, okay, the mean of this distribution is 3.5, the standard deviation is 1.708. It's clearly not normal, it's not a bell shape here, it's just a flat line. So if we looked at, they're going to do the same thing, looking at a distribution of 200 sample means from sample size 4, then do it for sample size 10, and then so what they're going to do is show as the sample size increases what happens to this distribution of the sample mean. So first, if we have sample size of 4, we already have somewhat of a bell shape, that the observations are already kind of centered towards the middle, the average of 3.5. But then as we get bigger and bigger sample sizes, we'll see that the exterior values are less and less likely because we're taking an average of a larger group. And when we have an average of a larger group, we tend to cluster towards the middle. And so this really comes out once we hit sample size 30, a nice uniform bell shape. And so what we find is that when we sample from a non-normal distribution, we want to, in order to make sure that the distribution of sample means is normal, we need to make sure that we sample at least 30. I'll say that one more time. If we want to make sure that the sampling distribution of X bar is normal when we're sampling from a non-normal distribution or any distribution, if we make sure that the sample size is over 30, we'll know that the distribution of the sample means will be approximately normal, which is good because we want things to be normal. We can make good predictions from that distribution. So what they're saying here is the mean of the sampling distribution is equal to the mean of the parent population. This is the same thing we said before, this part here. But the central limit theorem, this is the key point of it, is the shape of the distribution of the sample mean becomes approximately normal, more and more normal, more and more bell shape, as the sample size of n increases, regardless of the shape of the population, whether it be bell shape, skewed right, skewed left, or some other shape. And the minimum sample size that we can assure that the distribution of the sample means will be normal is 30. So if we sample over 30 from a non-normal population, we can be confident that the distribution of sample means is normal. So let me just check the other examples here. So they're just going through another example. I'll just show this. Basically, if we look at this, it says, suppose that the mean time for an oil change at a 10-minute oil change is 11.4 minutes with a standard deviation of 3.2 minutes. Now, the time for something for people to compute or to complete an oil change could be normal or not. I would guess that it's skewed right. I guess most times are short, but then some cars have some problems, so it's going to take longer than normal. So if we sample over 30, was what they're showing here, from a non-normal distribution, they say describe the sampling distribution of the sample mean. Well, since the sample size is large enough, over 30, the sampling distribution of X bar is approximately normal, and it has the mean equal to the population mean, that's still the same, with the standard deviation equal to the population standard deviation divided by the square root of n. So we just have to make sure when we're sampling from a non-normal distribution that the sampling or the sample size is over 30, and we can say that the distribution of X bar is normal. and then we can go through the problems like we did, like the example I showed earlier. Okay, thanks. We'll see you next time.